Vishay. Thank you for spending your time with us. I'm going to talk about GaN laser drivers for time of flight Lidar. So first, I'd like to give a special thanks to Dr. John Glazer, who does all of our, we call it heavy lifting. John is our expert in pulsed laser drivers. I've been involved with pulsed laser drivers now for over 10 years. Most of my work is directly with our customers. So just a reminder to everybody that lasers are dangerous. You can damage your eyes. So please take all of the eye safety requirements necessary. There's a couple of pieces to the puzzle of laser drivers for LiDAR. It starts with an optical pulse train, and I'll speak a little bit about that. Then there's the laser characteristics, which are somewhat less defined than we'd like, but we'll talk about some of the laser characteristics. And then we'll talk about laser drivers. We'll look at the fundamentals, some of the detail of the turn on of the laser driver. We'll look at a couple laser driver topologies, and then we'll look at detail of active turn off of the laser driver. From there, we're going to go and talk about inductance and layouts, and then we'll show some of the tools and the products that EPC has for laser drivers for LiDAR. So optical requirements, we work with both DToF and iToF. iToF is indirect time of flight, where there's going to be a very high frequency pulse chain. Today, the pulse chain is in the 100 megahertz range. In the future, it's going to go up to the 200 megahertz range. And from a current perspective, I mean, optical power and current are really the same thing. I'm in electronics, so I speak what I call electronese. I'm not that good in photonese. So in my world, the optical pulse chain is in current. So it's going to be a high frequency current on the order of, 10 amps or so at 100 megahertz, right? That's a little bit crazy. So you have to be, it's a difficult test to get there, and I hope to help you accomplish things like that. For DToF, it's going to be single pulses or a couple of repetitive pulses. These pulses are going to be in the tens to hundreds, and even up to, I've experienced 1,000 amp of pulse current, and these are going to be under five nanoseconds. So again, this is going to be a very difficult task. One, you need a laser driver that can get you these pulses, and two, you need to take very good care of the layout to get there. And I'm going to really focus a lot of my time on the layout to get there, and a little bit on the laser drivers as well. So laser characteristics. These curves are generic, and they're very similar for any laser you're going to find. You're going to have a current, and that's going to give you an optical power. Okay, so you're going to have a current versus optical power curve. So the necessary optical power will give you the current necessary to get that power. Now, with that current is going to be a voltage drop on the laser, and that voltage drop, it has to be considered in your laser driver. And then third, there's going to be an efficiency. As you increase the current, you're going to very rapidly increase the laser efficiency, and then it's going to fall off some. But the laser characteristics are a part of the circuit, and they have to be understood. And one of the things, and it's been getting better lately, is models of the laser have been slow to develop. So if you're in the laser business, or please accelerate the development of your models. And if you're a laser user, please ask your laser manufacturers to develop for better development of the models, because they can help predict the behavior of the system. So a laser looks like a diode, but it's more than that. It's going to be a circuit of inductance, resistance, and capacitance. Not only that, sometimes there'll be lasers in series. You could have multi-junction lasers, or you can have multiple discrete lasers in series as well. And then there's also areas where there's going to be lasers in parallel. And all of these combinations do add stray elements, particularly inductance, to the circuit. There's a couple of different ways to do lasers. There are edge lasers, and then there are VCSELs. But they're all, in the end, they're all lasers with the characteristics that define the V versus I and the I versus power of the devices. So they're inherently common cathode. So one-dimensional arrays are common cathode, but then multiple chips can be put on a substrate to have either a two-dimensional VCSEL array or just independent lasers. So lasers always have interconnects. They always have wire bonds. And the wire bond, and we'll see going forward, is very important in the circuit because at the speeds that we're looking at and the currents that we're looking at, the wire bond looks like an inductor. And we'll talk a lot more about inductance going forward. So for pulse laser drivers, there's two different control methods. Okay, one is what we call resonant control. And the resonant control has a small C laser drive, and then it's going to have a resonant tank formed with the laser pulse inductance. Now, the laser pulse inductance isn't there on purpose. You want it to be as small as possible, and that's going to be the stray inductance around that loop. So that stray inductance, you're going to want it to be on the order of hundreds of picohenries. And anybody that's worked in power electronics, hundreds of picohenries is very, very difficult to accomplish. So with the capacitance selected and the inductance inductance from your layout, you're going to have a frequency of the tank. And I'll talk a little bit more about this in the next slide. And then once you have the frequency of the tank, the voltage of the laser driver is going to be the knob that controls your power. For active turnoff, you turn on the device and you're going to have a large capacitance that's going to hold the voltage. And then at some point, you're going to turn off the laser driver, actively turn off the laser driver, which is going to cause the laser driver to interrupt the current for the turnoff. In that case, the energy in the stray inductance is going to transfer to the output capacitance, the COSS of the laser driver, and that's what's going to cause the voltage to increase, which will drive the current down to 0. So a little bit closer look at the resonant control. The C1 in this case is the laser driver capacitance. It's a small capacitance. It might be in the nanofarad type of range. And then your stray inductance is going to be in the hundreds of picohenries. And that's going to give you the resonant ring of the IDSL. So you're going to turn on the laser driver. The current's going to increase. It's going to go to a peak. At that peak, your voltage on the capacitor goes to 0. And then at that peak, it's going to ring back down. Okay, so it's very important to have low inductance for high DIDT, which gives you narrow pulse width. Uh-oh. So a little bit of the equations, and I'm not going to go through these in detail. They're well published. So the resonant frequency is going to be 1 over 2 pi square root of LC. The time is 1 over the frequency. And then the half amplitude pulse width is going to be determined by, by that as well. So you can use the calculations to get the answers to your characteristics. The peak current is going to be based on the V in minus the laser driver voltage over the characteristic impedance, which is again based on the inductance and the capacitance. So active turnoff, it works in a little bit different way. With active turnoff, you're going to have current going through the laser, And then once you turn off the laser, you're going to have the energy in the inductance is going to be delivered to the output capacitor. So this becomes the laser driver turns into a high impedance. And then so your turn off, what's going to happen is as the current goes into, and I'll speak up because I don't have a microphone, I'm sorry. As the current goes into the capacitor, you're going to get an overring. And here you have negative voltage across the inductor. So now the negative voltage across the inductor is going to drive the current down to zero. So fundamentals of whether it's resonant drive or active turnoff is if you ignore the stray elements, if you ignore the inductance, in a perfect world, you have your input go high, your VGS is going to go high, and your VDS is going to drop immediately. And with no inductance, your current ramps immediately. But on the left side is the perfect world. On the right side shows all of the different loops that are involved and all of the different stray elements of the circuit that's involved. So the question is what's that going to look like when you're working with tens to hundreds of amps and the IDTs in the tens to hundreds of amps per nanosecond, okay? And your laser driver is going to be in the tens to hundreds of volts. So it becomes really an RF circuit that you're working with, and a lot of care has to be taken in the layout of this to have your laser driver and system give you the edges and the peak powers necessary for your system. So I'm going to start off looking at the power loop inductance. The power loop inductance goes from your laser driver capacitor through your laser driver. And around the loop, there's inductance. So the laser power loop inductance is a lumped inductance consisting of the wire bonds, the traces, the interconnects, the ESL of the capacitor, and then everything else. And then there's another inductance that's referred to as the common source inductance. And this is very critical because the common source inductance is in both the laser driver loop and the power loop. Okay, but in this, I'm going to focus on the laser power loop itself. And we developed at EPC, John Glaser has developed some layout techniques where we have the laser driver, the cap, and the laser all on the top layer. So does this work? No, it's not going to show up. So what you're going to have is you're going to have the current go from the capacitor into the laser driver on the top layer, and then you go into the second layer to return to the laser driver, and then the loop is completed when the current goes back to the capacitors. Now, what's most important about this is the inductance. So what we want is very, very narrow spacing in between the top layer and the second layer. Okay, and that's going to help cancel most of the inductance in the circuit. Now, from a top view, which is shown down in the bottom, we want very, very wide traces to minimize the inductance. So you can see both the top view and the side view of the power loop to minimize the power loop inductance. When you do a layout for a laser driver for Lidar, this is where you start. Okay, this is the basic fundamental that you have to get right, and everything else has to go around this. Okay, this is where you start your design. Okay, so the laser driver itself has to have a high peak current. Okay, it has to have very fast switching, and the fast switching has to do with the parasitic capacitances of the laser driver. These consist of the gate to source capacitance, the gate to drain or Miller capacitance, and also the output capacitance. Okay, in addition to the power element, you're also going to have the gate driver of the power element. Now, in some cases, these are integrated together, and in some cases, they're separate with a discrete FET and then an integrated circuit gate driver. The gate driver also looks kind of like a laser driver, where again, you need a high peak current to charge the capacitances in the gate. And you do need low resistance and low inductance to be able to very quickly turn on and off the laser driver. So the integrated laser driver gives you the best performance, primarily because it reduces the gate drive inductances of the circuit. So this is taking a look at some of the EPC's AEC Q101 qualified power FETs. And what we have is an assortment of FETs from very low peak current capability to high peak current capability. They range from 20 amps, and in fact, we have some that are lower than 20 amps, 20 amps to 390 amps. Now, what you want to do is you want to select the laser driver that has the correct peak current. For example, if you have a 70 amp capability, you don't want to use a 125 amp laser driver, because the higher the current, the higher the capacitance, and the slower the laser driver is going to be. And also, the higher current has a higher cost. So everybody wants to use the lowest cost possible. So the best solution gives you use the lowest possible peak, the device with the lowest possible peak current for your application. Okay. The QoSS of the FET is an important characteristic, because the QoSS, the discharge of the QoSS, it shares a path with the laser driver. So going through the channel of the laser driver, you're going to have both the laser current and the discharge of the COSS. So what you want to do is you want to collapse the VDS very, very quickly, and that entails discharging the COSS. And that's also, again, why you want to use the smallest device possible, because that smallest device has the lowest COSS. And there is an equation that estimates, there's a lot of assumptions in the equation, but it does estimate the time associated with the COSS discharge. And it involves the QoSS, the gate impedance, the gate drive loop impedance, the CGS of the FET, the transconductance of the FET, the VDD, and the VGS at the discharge point. And that's taken from the transfer characteristics curve. Okay, in terms of gate drivers, a lot of the drives are done with the LMG 1025Q1 from Texas Instruments. It is an AEC Q101 qualified device, Q100, I'm sorry, and it's a 7 amp pull up and 5 amp pull down. Now, it does have wire bonds as terminals, so it does have some inductance, but it is an excellent gate driver, and it is automotive qualified to go with the AEC qualified EPC devices. So looking at the gate drive loops, the gate drive loops are going to include wire bonds. It's going to include solder bumps, and it's the blue trace coming around here for turn on. Okay. Now, again, the one that's going to be the most critical is common source inductance, and I'm going to talk about that specifically because it's extraordinarily important to be able to keep your common source inductance low, because your common source inductance voltage across it reduces your gate drive voltage. Turnoff is the same, basically the same thing, but just a little bit of a different route. It does not include the capacitor. So common source inductance, if you consider that your power loop, you're looking for around 100 amps per nanosecond, that 100 amps per nanosecond is seen across the common source inductance. So if you have 100 amps per nanosecond, even if you have as low as 50 picohenries of common source inductance, basic electronics says V equals LDI dt, and your gate drive, your common source voltage is going to be 5 volts. Now, if your drive voltage is 5 volts and your common source inductance voltage is 5 volts, you have no potential to charge the capacitor. So you can never get to your desired 100 amps per nanosecond. So you have to do better. So the typical DIDT is going to be about 100 amps per nanosecond, 50 picohenries, gives you 5 volts of drop, which is not a good way to do it. So for the switching time associated with common source inductance, it's approximated again by common source inductance times the current requirement over the VDD minus VGS. Now note that the VGS is the VGS inside the device, and that VGS is determined by current on the data sheet from the transfer characteristics curve. So now we're going to talk about optimizing the layout to reduce and almost eliminate the common source inductance. And again, this is work that was done by Dr. Glaser. And this shows what's going to be a new release of one of our demo boards. And you're going to have the basic laser drive loop, which is shown in the on the left side. And then you're going to have the components of the PCB as shown on the right side. Okay. So what we're going to have is the current is going to go from the capacitors into the laser and then return on the second layer. Okay. So what we want to do is we want to minimize the common source inductance. So in this case, the gate drive loop goes in the opposite direction of the power loop, as shown by the red arrow. And then you're going to have the load current is going to go in the opposite direction. So the only common source inductance that you're going to have is in the solder bumps of the laser driver itself. Okay, so within the laser driver, and then once you get to the board, you've got power going in one direction, you have gate drive going in the other direction. That's actually considered negative common source inductance, which is going to help your switching. Okay, and then in the second layer, your return to the laser driver is going to be in the second layer. And again, it's going to be outside of the gate drive loop. Okay, so with this layout, we're able to get in the 10 to 20 picohenries of common source inductance on a standard PCB. So you don't need an expensive PCB. We do use via in pad to be able to keep the inductance of the vias very low, but we don't need laser vias. We don't need really special vias. So it is a very cost-effective manufacturing system. So a little bit about integrated laser drivers now. Integrated laser drivers, the fundamental is that they reduce the inductance, particularly the common source inductance and the gate loop inductance of your laser driver. And it eliminates most of the common source inductance. It eliminates all of the wire bonds and many of the other interconnects. The only external path is through the capacitor, the power capacitor. So it's good. This is, you know, the laser driver ICs are going to give you the best performance. They are going to be much smaller. They are going to be less expensive. So it's really going to be a very good win for the designer by using a laser driver IC as opposed to discrete components. So the laser driver family of ICs that EPC currently has, we have 3 devices that have been released to the market, EPC 21601, 603, 701. They're all 15 amp laser drivers. We do have 2 of them coming up within the next few months. One is a 30 amp laser driver, and then one's a 75 amp laser driver. And if you look at the size, these are all quite small. You know, a 75 amp laser driver that's 5 millimeters square, then that's going to give you the best possible performance of your laser driver circuit. A couple of the development tools that EPC has, we have a number of demo boards. The demo board, we are going to be releasing some new demo boards with the new laser drivers, and also some of the new discrete devices will have new demo boards also. So the power part of the demo board is the loops, the gate drive loop and the power loop. The board is much bigger than shown on here because we also want good measurement points. The measurement points are built in, that the RF terminations are built in so that you can get very good accurate measurements and understand what your laser is doing and then measure your laser output with these. Currently, they run from 10 amps to 214 amps. So looking at them a little bit differently, we do have products and tools. We have 9126 and a high current version. And then we also have a higher power version, 9150. And these utilize the devices shown. And then the red devices are all our AEC Q101 qualified parts. Now, if there is a device that you don't see up here that you'd like automotive qualified, please contact your local EPC FAE, and then we'll work to build a business case to run the qualification. Most of our parts, we will be able to do an automotive qualification. So in conclusion, there are many laser implementations with common application requirements. So what I described here applies to every laser driver circuit for LiDAR that you will have. Okay, so please use the suggestions to get the most out of your circuits. EPC technology, the GaN technology, has very low capacitance, very low inductance, and it's going to give you the extreme speed needed for laser drivers for LiDAR. ICs are going to further increase performance, reduce size, and reduce cost of your system. So as we come out with new laser drivers, please take a look at them and evaluate them. Reduction through careful layout has to be on the top of your minds. You start with the laser driver, then you do your gate loop, and then you do the rest of your circuit. Common source inductance can be nearly eliminated, and then EPC has demonstration tools for your LiDAR system development. I thank you for your time. I don't know if we have time for questions, but thank you, and Wan De Kaixin.
感谢史蒂芬·克林诺专家的精彩发言。请问下面有什么问题需要询问的吗？你好，那个克林诺先生，我想请教一下两个问题哈。第一个问题是这个，在我们这种 capacity 的这种方案当中，如果我在那个放电结束之后，由于过充会有一个小的一个电流脉冲，再给到我的这个 LD。 这个可能会让激光超过它的阈值，然后这个问题的话，您这边是怎么建议我们去解决呢？然后那个第二个问题是我们现在已经有了一些这个集成的芯片，那是否有多通道的芯片？然后或者说我们在多通道芯片的开发过程中有什么困难或者问题？希望您能解答一下，谢谢。
First question is for the resonant control. So after our FET turns off, there is a circuit to charge the capacitor again. I think maybe a booster circuit. So if the booster circuit has a very high DVDT, maybe the current will charge our COSS also. Then the laser will turn on, will light again, and the laser has a ITH, the threshold current. So do we have any suggestion to avoid this issue? This is the first question. Yeah.
Yeah, and yes, thank you for your question. It is an issue, and that's part of your charging design. Is you're going to have to keep you have a lot of time to charge, so you can charge very quickly with a high current, which will go through your COSS, or you can take longer to charge and keep your current through the QoS lower. But it is a concern that you do have to be aware of in your design. So thank you.
第一个问题的回答就是因为我们的谐振式控制方式采用充放电给电容充放电嘛，然后通过这个电容的放电来驱动这个激光器的点亮啊。那么在这个过程中呢，刚才您提的这个问题呢，它是来自于重新充电的时候，因为我们很多客户考虑到这个充电的速度以及这个系统的效率啊，会采用这种有源电路来进行充电。那么这个充电速度呢，会对我们这个管子的输出节电容有一个充电的效果啊。就刚才说的这个充电是指给那个V84的电容充电，同时这个充电电流也会给我们的这个，就它如果充的太快的话，那么这个 DVDT 会给我们的 COSS 也充电。这个时候电流如果就是我的 COSS 充电电流如果超过了 laser 的这个阈值电流的话，它就会被点亮。 所以这个时候只能控制这个充电电路的速度。但是呢，因为根据我们的一般的应用呢，它这个特别像 ToF 这种应用啊，它属于这个点亮的时间特别窄，但是呢，这个重屏的这个时间是比较长的。那么我们建议还是降低这个充电速度，因为在这个 turn off 的期间有足够的时间去充电啊，这是一个方式啊，主要也是在这个充电电路上面想办法。So second question is, do we have any plan to do some multiple channel GaN IC, not a single IC?
There multiple channel ICs are, I mean, we have the capability. Today, we don't have a plan. We can do it if we have a good business case. So if you're in need of something that is beyond, and one of the things we're trying is to keep the width of the device narrow. So you can use single ones in next to each other. But we certainly could. We don't have them on the plans today.
就是在这个多通道的 IC 的这种方向上，现在最大的一个问题就是，如果我们把它做成一颗多通道的 IC，那这种情况下，在通道之间啊，需要做绝缘。做绝缘，也就是说，我们会牺牲一些这个芯片尺寸去处理这个绝缘的问题，那么带来的成本和空间的上升。那么我们很多客户呢，特别在激光器，就是多通道的或者阵列激光器的这种应用下呢，需要非常窄的这个 pitch 啊。那这种情况下呢，还是以这个单芯片，就是单颗的 GaN IC 为主。那么因为客户把它勒在板上之后，可以通过 layout 啊，让它之间留出一个空间出来，就是比较方便使用的。当然成本也会相对来说比较低嘛。但是呢，我们不排斥啊，在一些应用下，如果有非常好的这个商业案例的话，我们也可以去讨论。但是这肯定是基于某一个具体的商业案例的啊。
好的，好的，感谢您的回答。
还有人需要提问吗？
Hello, Collins. Is it possible to integrate the drivers with the sensors? I mean, sensors is a low voltage and low current, but the drivers integration with the sensors, and then we send a command from the sensors to control the VCSEL or other laser diodes. Is that okay?
The GaN technology is it's an analog high power technology. The sensor technology is a low voltage, very different technology that needs a lot of processing capability. The laser loop, the inductance and the layout of the laser loop is so important. You really want those two functions separated. In fact, we've had discussions about possibly integrating the boost. And the answer is the inductance of the layout is so important in the laser driver to the function of the Lidar system that you want that to be all together. And the boost can be over here. That's okay. The detector is a different technology. So I don't think that those are going to get integrated unless they become integrated on package, but you still need to have, the detector has to get the light coming back. So it's going to be two paths. One is going to be out, one is going to be back, and they really have very different functions.
That's my question, because there's some customers are asking us or the industry. So do you have any requirement from the customers like this?
We haven't, we've had all kinds of questions from customers. And so with the detectors, not really. We've been asked to integrate the laser with the laser driver. And for that, we really have to rely on, part of the laser is also the optics. So that's really going to fall onto the laser manufacturer to come up with the module with the optics. And there has been discussion about laser manufacturers integrating a laser driver with the laser, but not the detector.
Thank you.